All right, recording in progress. And go back to try to share the screen of where we were. All right. So I was just about done with 1.3. I'll finish up 1.3, sneak in some of 1.4. Again, this calendar is messed up now, but that's actually to our advantage. There is no 1.5, as I indicated here, but I didn't indicate on the other side, which means I have extra time to play with, as it were. So I can afford, not that I'm planning to, but I can afford to fall behind a little bit, so to speak, because I missed that up over there. Yes.
I was doing the homework yesterday, and could you okay, so tangent to the y or x-axis means that it just sits on top of it or right next to it, right?
Yeah, I was actually going to show you that, but I think I know which one.
I thought you went past. Okay, I'm sorry. I thought you went past it yesterday, so I asked.
Yeah.
Okay, cool. Okay.
That's good. So yeah, let me go ahead and show you that particular problem. I think I know what I'm talking about, but if I'm not, then you can go ahead and ask again. Okay. All right, so we're back to 1.3. We were doing 1 to 61, I think. Okay, and I think I showed you the problems before, again, for those of you that don't have the book and aren't getting it, but I'll show you the problems one more time just in case. And there we go. All right, so yesterday we got up to 45, so I believe this was the last thing that I did. I usually mark it off with the double lines here. So this was 1 less than x squared plus y squared less than 4. A nice way to think of this is it means you want the radius to be between 1 and 2. Okay. X squared plus y squared equals 1. Center of the origin, radius of 1. X squared plus y squared equals 4, radius of 2. So when it's like that, you're basically saying you want the radius to be between 1 and 2. So here it is, between 1 and 2. A dotted circle, radius is 1. Dotted circle, radius is 2. So everywhere in between, your radius is between 1 and 2, right? So like radius is 1.1, 1.5, 1.9. Another way of saying it is you are 1.5 units away from the origin, 1.9 units away from. So this is a set of all points. These are all the points in the XY plane that are between 1 and 2 units away from the origin. That's another way of thinking of that. Or give me all the points that are between 1 and 2 units away. So here they are. Like this is 1.5 away, or 1.9 away, or 1.1 away, and so on. All right. Okay, question 49. You're asked which point is closer to the origin between the two given points. So which of the points -7, 2 and 6, 3 is closer to the origin? So the origin is 0, 0. I just use the distance formula from each one to 0, 0. 0, 0. So distance formula, -7, 2. The distance is the square root of -7 minus 0 squared, right? Subtract the x's, we can say delta x, square it, plus delta y squared, 2 minus 0 squared. So -7 squared is 49, 2 squared is 4, square root of 53. And I do the same thing with 6, 3. So how far is 6, 3 away from 0, 0? So the distance is the square root of 6 minus nothing squared plus 3 minus nothing squared. So 6 squared is 36, 3 squared is 9, radical 45. And yes, you could simplify that radical by taking out a 9, but you don't really have to. You're just looking at these two, right? Square root of 45 is smaller than the square root of 53. So final answer is 6, 3 is closer to the origin. And this is how you would do it, showing me the distance between the two. So reminder, we are doing this formula. Distance is square root of x2 minus x1 squared plus y2 minus y1 squared. Page 16. Put it on your formula sheet. Put it on your cheat sheet if you would. Okay. And yes, I see something in the chat. Let me get this first. And this may be the question that you're asking for. 3,7 tangent to the y-axis. Okay, tangent means you just barely graze it. Okay, so 3,7, you should get that. 3,7, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, right? Okay, now tangent to the y-axis means it's like this. It just barely grazes it. Okay, it doesn't come way out here. Okay, if it comes way out here, it would touch the y-axis twice. And it's not inside. Okay, so for a circle to be tangent to the y-axis, it's going to touch exactly once in exactly one point. So it's just like so. Okay, so if I come way out here, it's going to touch at 2 points. If I make it too small, it's not going to touch at all. So tangent to the y-axis, in this particular case for a circle, it means it just touches at 1 point, just grazes it. And that tells me that if that's going to happen, the radius is 3. So that's basically the setup. So translation of this problem, center is 3, 7, the radius is 3. So there we go. X minus 3 squared plus y minus 7 squared equals 3 squared, which is 9. Right? X minus 8 squared plus y minus k squared equals the radius squared, which is 9. So again, this is an application of this formula. And again, put this on your cheat sheet if you wish. And where is it in the text? Page 17. Okay. The point xy lies in a circle with center hk. So if the center is hk, the radius is r. Here's the equation. X minus 8 squared plus y minus k squared equals r squared. Okay, so that's how to do that one. Let's see. And a quick question about 53. Okay, I'll do it if I can get back to it. Oh yeah, I see that one. Okay, I'll get to it if I have time. But yeah, I wanted to go on with the other ones that I was going to show you. Okay, 47. X squared plus y squared is less than or equal to 4. And y is greater than or equal to x. X squared plus y squared equals 4. Circle, center of the origin, radius is 2. There's a line underneath it, so it's solid. And now less than or equal to means inside. Okay. So if I didn't see this, I'd be shading all of this, right? X squared plus y squared equals 4 is this circle. Less than or equal to 4. That's everything inside. So why don't you just shade everything inside? Well, because it says y is greater than or equal to x also. Y equals x is this line. It's solid. Greater than means above. So essentially, you're saying everything inside the circle, but it has to be above the line. So that tells me to shade only this portion right over here. Okay. So that's what I do for 47. Okay. And 61, and yeah, I was going to be done with the section. So yeah, I can go ahead and answer, I think what was it, 53? Yeah. Okay, 61. Find the area of the region that lies outside the circle x squared plus y squared equals 1. That's a circle, center of the origin, radius of 1. Inside the circle, x squared plus y squared equals 9. Circle, center of the origin, radius of 3. Here's a picture. Circle, center of the origin, radius of 3. Circle, center of the origin, radius of 1. So formula for the area of a circle is pi r squared. A of a circle, area of a circle, pi r squared. If you want to put that on your formula sheet, you may. I'm sure you probably heard that before. So it's pi bigger radius squared minus pi smaller radius squared. So pi bigger radius is 3. So pi times 3 squared minus pi times 1 squared. That's 9 pi minus pi. 8 pi is my answer. Okay. All right. I was done with 1.3. I was going to start 1.4. So yes, it would be appropriate for me to go take up one of the questions about 53. So 53. Find a fourth point that will form the vertices of a rectangle when added to the points in exercise 51 is the point unique. So go back to 51. Negative 1, 4, negative 3, negative 4, and 2, negative 1. Okay, so we're doing 53. I'll call them A, negative 1, 4. B, I'll say is negative 3, negative 4. And C is 2, negative 1. So find a fourth point so you end up with a rectangle is the point you need. Okay, so what are they talking about?
I was particularly confused because 2 of the sides already are equal, so I didn't really see how I could form a rectangle with that, but I
Okay,
want to see how you do it.
all right, so let's plot these points. Okay, negative 1, 4, negative 1, 4. Negative 3, negative 4. 1, 2, 3, 1, 2, 3, 4. 2, negative 1. 1, 2, 1. Okay. So now it says what? Whoops. Where'd it go? Find a fourth point that will form the vertices of the rectangle and add to the points exercise 51 is the point unique. All right. So how do I make a rectangle? So that means we already have this. Whoops. So eyeballing it, maybe it's here somewhere. Right? So maybe it's going to be here. This is what I'm trying to figure out.
That's what I first thought, but B to C is has the same length as A to C. So that is why that doesn't really make a rectangle. You know what I mean?
Okay, BC should be the same as
No,
AD.
BC,
Is that what you're saying?
BC and AC have the same length.
They have the same length. Yeah, that could be. That's fine. In fact, did we? Maybe you can save me some time. What was that length that it came out to be?
Square root 34.
Let's see. A to C, radical 34. That's correct. And C to B is also radical 34, right?
Yeah. So they're asking for a rectangle. So I don't know, like it could be on the opposite side. That'd be very odd. It would be kind of a sideways rectangle, but like rectangles are supposed to have two different lengths. You know what I mean? Like length for the sides and length for the top and bottom are equal, right?
Yeah, they don't have to be. Evidently, in this case, it's going to turn out to be a square.
Okay. All right.
So a square qualifies as a rectangle.
Okay. No.
So that's allowed. Okay.
So how would you find that point? Yeah.
Right. So how do I find this point now? So let me call it X comma Y.
Can you use the midpoint between A and B?
Come again? Can I do what?
The midpoint between A and B?
The midpoint between A and B, like over here?
Yes.
Well, that would not give me a
Or,
rectangle.
or maybe the distance between A and B, which is the hypotenuse.
That would give me the hypotenuse, yes. I'm not sure how that's going to help here, but
I was thinking using the distance between like how the distance between B and C like put a variable in for this point for the distance formula to have it equal square root of 34.
that's right. That is the way to do that for the most
Okay.
part. Okay, so let's see. Yeah, what was this again? -3, -4. There's actually more than one way to do this. And A was -1, 4. Okay, so as somebody mentioned, distance from here to here should also be radical 34, and this should also be radical 34. Is that right? So that means x minus a -1 squared plus y minus 4 squared equals radical 34 squared. And likewise, the distance from here to here should also be the same thing. So that would be x plus 3 squared plus y plus 4 squared is equal to 34. Okay, that might come out to be a little bit messy. Let me go ahead and try that. But anyway, both of these have to be true, right? So let me try to clean this up. X squared plus 2x plus 1 plus y squared minus 8y plus 16 equals 34. Now this might come out to be a mess, actually. And that's saying the same thing as x squared plus 2x plus y squared minus 8y. And that's going to be 17. Yeah, I'm not sure if this is really going to help a whole lot in terms of approaching this. Yeah, this can work, but I
Could
can
we
see it's gonna
complete
be
the
messy.
square to figure it out?
I'm sorry?
Could we just complete the square to figure
Completing
it
the
out?
square, we're just gonna come back to this. We're just gonna retrace our steps. So we'll just come back
Right,
over
yeah,
here.
right, I see.
Okay, I think a better way to approach this would be going by slopes. Okay, and so rather than doing this, I think it'll work, but it's messy. I would approach it by slopes. So let me find a slope here, and the slope here would have to be the same, and likewise this direction. So let me call this M1 is, I forgot what was C, 2, -1. So the slope here is 4 minus a -1 over -1 minus 2, which is equal to -5/3. And so that means this has to also be -5/3. And I believe we showed these were perpendicular, right? That's part of the problem. These are perpendicular, which means this slope would have to be 3/5. Whoops. Let me see if that's actually the case. -1 minus a -4 over 2 minus a -3. And yes, that is 3/5. Okay. What I'm aiming to do is find the equation of this line, the equation of this line, and then find their intersection. I think that's easier. Okay, so maybe I'll call this L1 and L2.
Wouldn't it be -5 halves because 4 minus 2 is 2?
Okay, where are we here? This one right here?
Yeah, for the slope, wouldn't it be -5 halves because 4 minus 2 is 2 and not 3
Where is 4 minus 2?
for the
I'm
slope?
trying to find a slope right here. Sorry, 4
For
minus a
M1.
-1 over -1 minus 2.
Got it, it's a -1 minus 2, never mind.
Yeah, -1 minus 2. Sorry, my writing is bad sometimes. Okay, so I'm going to use y minus y1 equals m times x minus x1, the point slope form. So this I'm going to call line 1, L1. So here's a point and the slope was negative 5/3. Okay, so y minus a negative 4 equals m negative 5/3 x minus a minus 3 y plus 4 equals negative 5/3 x. Okay, so I'm going to make this a double negative. So if I distribute, that's just going to be negative 5, right? So minus 5, subtract 4, y equals negative 5/3 x minus 9. And let me just double check if I plug in negative 3, it's 5 minus, yeah, it works. So this is line 1. Do the same thing for line 2 and find out where they touch. So the point is negative 1, 4.
Oh.
Slope is 3/5.
So you use the point, you use the point negative 3, negative 4 because that's on the line that we want, and you use the slope of the opposite line because they have the same slope.
These two have the same slope, correct?
Okay,
If you have a rectangle, they're parallel. So this slope has to be negative 5/3, and this slope has to be 3/5. So I use this slope and this point now. Okay, so I'm going to use that and that. So y minus 4 equals 3/5 x minus a minus 1, which is x plus 1. Okay, so the point was negative 1, 4. So x minus a minus 1, 4, and the slope is 3/5. Okay, do the same thing. Y minus 4 equals 3/5 x plus 3/5. Add 4. Add 4, which is like 4 over 1. Multiplied by 5, multiplied by 5. So y equals 3/5 x plus 23 over 5. It's very messy. Let me see if that actually works. I plug in negative 1, I get 4. Yes, it works. So this is line 1. This is line 2. And now I just have to find out where they touch. And that'll do it. Okay, so line 2, I found out has this equation. Line 1 has this equation, so I find out where they touch. It does look messy, but it seems to be much nicer than trying to go through all this mess.
Can you let me look at your equation really quick and how you got there? Push it up a little bit. The negative 3. Wait, why isn't that negative now? Isn't that a negative 3/5? Oh wait, no, it's not negative 3/5. I'm sorry, I'm backwards. Okay. Yeah, just let me look at your answer really quick and let me see here. And so, and then you added 4 over 1.
I'll hold it here for a moment. I know there's a lot of stuff going on. Okay.
Okay.
I'll come back up here if you need this also. All right, so now I just find out where they touch, which means I set them equal to each other. So 3/5 x plus 23 over 5 equals negative 5/3 x minus 9. So I set this equation equal to this equation, find out where they touch. Okay, I don't like all those fractions, so let me multiply both sides by the common denominator, which is 15. 15. Distribute, 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 distribute. So 15 divided by 5 is 3. 3 times 3 is 9, 9x. Plus 15 divided by 5 is 3. 3 times 23, punch it in the machine, 69. 15 divided by 3 is 5. 5 times negative 5 is negative 25. 15 times 9, punch it in the machine, 135. I forgot the X here, sorry.
Wait, oh, I see what you're doing. Okay. You're times it by 15 for the common denominator. Okay.
I multiply both sides by the common denominator because I don't like the fractions.
Yeah.
Okay, so I'm going to add 25x. And while I'm at it, subtract 69. Here. Yeah, this is kind of unfortunate. If we were meeting face to face and we were on a board like a whiteboard, you can see the entire whiteboard, but on my document camera, you can only see little snippets. So add 25x, that would be 34x. And then on my calculator, negative 135 minus 69. 204. Divide both sides by 34. And x is equal to 6. And then I plug in to find y. I'm plugging in here.
Shouldn't it be -6? Because look at the graph. I mean, look at where it's plotted. How is our point going
Negative
to be x?
204. All right. I goofed.
Yeah.
-6. Right. I forgot the negative. Okay. And how about I plug it in here? Negative 5/3 times -6 minus 9. So that's going to be 10 minus 9, 1. -6, 1. So yes, that was quite a bit.
Beautiful, thank you. I see that when you want to find where two lines touch, you just make them equal to each other.
Yes.
Actually, no, I understand all, but I have no questions. Thank you.
Okay. All righty. I'm actually theoretically done for the day, but we have plenty of time. I'm going to sneak in very little of the next section. Well, actually, I would not have been done, but the fact that we're not doing any 1.5. Yeah, I was scheduled to do some of 1.4, but I can afford to not do as much because there is no 1.5. So I'll introduce some of 1.4 right now. So we'll go ahead and do that.
Would we ever see an equation like 53 on an exam or a quiz?
Okay, something like 53 on a quiz or an exam. Now, for an exam, you only have an hour. This problem itself takes a long time. So I would probably not have you do that entire problem for an exam. Now, for a quiz, since you have so much time, I'm actually more willing to give a problem like that in a quiz since you have many hours to do a quiz. But for something like that, and you're limited to just finishing everything within 1 hour, probably not the whole thing. Okay.
Okay, cool.
Yeah. All right, so 1.4, we're introducing equations and graphs. And one of the first things we need to introduce is the concept of symmetry. Okay, so how many problems are on an average exam? I usually give about 10 questions on an exam. So 10 questions, 50 minutes. Right, so that would be what, 5 minutes per question on the average? All right, talk about symmetry on page 25. Here's a graph of y equals x squared. This graph has symmetry with respect to the y-axis, or sometimes we say y-axis symmetry. Symmetry with respect to the y-axis. So if I kind of put a line right on the y-axis, imagine this is a mirror. You get the reflection on the other side, right? The reflection of this side becomes this side, and so on. Okay, so if you have the point 2, 4, you automatically have the point 2, -4. If you have 1, 1, if you reflect across the y-axis, you get -1, 1. So this graph has symmetry with respect to the y-axis. You can have x-axis symmetry, symmetry with respect to the x-axis. So they have the graph x equals y squared. So if I imagine putting a mirror on the x-axis, right? Again, you see the reflection, so to speak. This graph reflects across to this side. So you have 4, 2 and 4, -2, 1, 1, 1, -1. So any point on the graph reflected across the x-axis will give you this corresponding point.
This could be considered like this symmetry between y equals x squared and x equals y squared. Is that considered like an inverse of a function?
Are the inverse functions? Sort of. Okay. I mean, this would not be a function. I know what you're talking about. And that's a good concept that you have. Okay, but this technically is not a function. But yeah, in
No,
some sense, that
because
would
it
be an
doesn't
inverse.
pass the line test. Yeah.
Yeah, we'll talk more about inverse functions later. But yeah, that is
Got
a good concept that you have. But for now, for inverses, they have to be a function. And you might recall, this is not a function. It does not pass the vertical line test.
Yes.
But hold that thought. It is a good thought. But yeah,
Thank
they
you.
are inverses in some sense. All right. Origin symmetry, page 26. The graph of an equation has origin symmetry. Okay. Now, what is origin symmetry? If you reflect across the origin, so if you have this point x, y, and go across the origin to the point -x, -y, then you have another point on the other side of the origin, so to speak. So whenever you have x, y, you have -x, -y. So this would be origin symmetry. This point here, if you bounce it off the origin, it comes down to here. Or this point way at the end here, reflect across the origin, you get a corresponding point over here. That's origin symmetry. Okay. This circle here has all 3 symmetries. It has symmetry with respect to the y-axis, right? If you take this semicircle and reflect, put a mirror right where I'm at, and it reflects over to here. So symmetry with respect to the y-axis. It also has symmetry with respect to the x-axis, right? The top half of the circle, imagine reflecting across the mirror here, and you get this part. And you also have origin symmetry. If you would take any point and go across the origin, you get a corresponding point here, or this point here reflects over there, or this point here reflects over there, and so on. So this circle, as you might imagine, the circle is nice and symmetric. It exhibits all 3 symmetries: symmetry with respect to the x-axis, y-axis, and origin.
So in this circle, technically speaking, the spatial angles, they have symmetry on different quadrants, though.
The language we would say is symmetry with respect to the x-axis, y-axis, and the origin. But yeah, I mean, you can consider what happens in the quadrants. Okay. Like here it looks like quadrant 1 and quadrant 2 mirror image. Quadrant 1 and quadrant 4.
Because I see on the circle on quadrant 1 and quadrant 4, right? So there's
Quadrant 1
a
and quadrant 4,
symmetry.
yeah, there's symmetry there. There's also symmetry with
Yeah.
quadrant 1 and 3, and
Yeah.
even 1 and 2.
That's
Which
the
almost means-
30-degree angle.
Yeah, we're not there yet, but yeah, we'll talk more about angles when we get to trig.
Yeah.
Yeah, but as far as symmetry is concerned, right, if you only have the first quadrant, like suppose you only saw that quarter of a circle.
Yeah.
You can draw the rest of it, right? By symmetry.
Uh-huh.
So you know that part there, you can just say, oh yeah, if I reflect across the y-axis, I got that. And now that you have that, you can kind of flip that over and get this whole thing. So it's almost like if you only have this quadrant 1 stuff,
Got it.
and it has all the symmetries, you can generate the rest of it.
Yes.
Uh-huh. Okay, then on page 26, this graph looks like it has y-axis symmetry. Sorry, I can't make the any bigger, but yeah, symmetry with respect to the y-axis. Put a mirror here. You have the reflection across the y-axis. So if you have a point x comma y, notice you also have the point negative x comma y. And that's true all throughout. X-axis symmetry, x comma y, x comma negative y. Here's absolute value function. Remember the absolute value function? It looks like a V. It has what kind of symmetry? Y-axis symmetry.
Yeah.
Right?
Yes.
It does not have x-axis symmetry, because if it did, you'd have something down below, but you don't. So it does not have x-axis symmetry. You do not have origin symmetry either, because if you have this point here and bounce it off the origin, you should have a point down here, but we don't. So we don't have origin symmetry. So it looks like we just have y-axis symmetry for this particular graph and nothing else. Okay. All right, now, how can we determine symmetries? So 1.4. So here are my examples again, and the book goes over these. Y equals x squared, y-axis symmetry. So like 2, 4 reflects to negative 2, 4. X equals y squared, x-axis symmetry. So 4, 2, 4, negative 2. Origin symmetry, like y equals x cubed. Y equals x cubed looks like this. So you have 2 comma 8. Make them both negative. Negative 2, negative 8. By the way, notice what happens when you plug in 2. 8, right? How about negative 2? What's negative 2 cubed? Negative 2 times negative 2 times negative 2 is negative 8. So you have origin symmetry. So how do I tell if I have x-axis symmetry, y-axis symmetry, or origin symmetry? Okay. The book kind of implies it when you give this language. It might be kind of hard to understand what it's talking about. It's true. The graph of the equation has y-axis symmetry if negative xy is on the graph and xy is on the graph. It's true, but you're saying, huh, what are you talking about? And likewise for x-axis symmetry, it's correct, but what does it mean? And likewise, origin symmetry, negative x comma negative y is on the graph whenever xy is on the graph. That's true, but how do you actually figure it out? So here's my little algorithm for that. And you can put this on your cheat sheet if you wish. And again, if I'm doing this too fast, you can always go back and watch the video. So they give me an equation, right? Again, I don't know, y squared equals x cubed or whatever. How do I know if it has x-axis symmetry, y-axis symmetry, or origin symmetry? Okay, so here's the technique. If you have some relation, replace x with negative x. In the equation, wherever you see x, put negative x. If we get an equivalent equation, we have y-axis symmetry. If you replace x by negative x and you get the same thing back, y-axis symmetry. And here's an example. Y equals x squared. We said we have y-axis symmetry. So how do you know? Okay, I replace x with negative x. So y equals x squared, change it into negative x squared. So this x right here, make it negative x. But what is negative x squared? Same as x squared. So I get the original equation back. I get an equivalent equation. That tells me that I have y-axis symmetry. Okay. Hopefully this becomes more clear when we do some problems, and I'll start problems tomorrow. Okay. Okay, for the other symmetry, well, this one I replace x with negative x. Can you guess what's going to happen for the other type of symmetry? Replace y with negative y. If I replace y with negative y, if we get an equivalent equation, we have x-axis symmetry. Yeah, this is kind of weird because if you replace x with negative x, at first glance, you might say, well, I'm doing x, I should have x-axis symmetry. No, it's the other letter. You have y-axis symmetry. And likewise, if you replace y with negative y, you don't have y-axis symmetry, you have x-axis symmetry. But if you look at the picture, it actually makes sense. But let me actually go through the mechanics of this. So x equals y squared. Change y to negative y. X equals negative y squared. But what is negative y squared? It's the same as y squared. And I do get the same thing as my original. So I end up with x-axis symmetry. And yeah, that is borne out. So what I say here, it may not seem like it's intuitive because it says x here, but you have y-axis symmetry. And it says y here, but you have x-axis symmetry. Well, let's look at the picture. This one has y-axis symmetry. Because if I replace x with negative x, I get something equivalent. And likewise, x-axis symmetry. Okay, I replace y with negative y, I get another point in a graph essentially. So they are going to be equivalent. And yeah, let me get this. I know there's a question in the chat. I'll get to it in a second. But for origin symmetry, you replace both of them. Replace x with negative x and y with negative y. If we get an equivalent equation, we have origin symmetry. So put all this in your cheat sheet. Replace x with negative x only. If you get an equivalent equation, y-axis symmetry. Replace y with negative y, get an equivalent equation, x-axis symmetry. Do both of them. Replace x with negative x and y with negative y. If we get an equivalent equation, we have origin symmetry. Okay, let me show you how that works here with y equals x cubed. Y equals x cubed has origin symmetry. So change y to negative y.
Wait, why does negative y, why is that equivalent?
Okay, so let me go through the process. Change y to negative y.
Yeah.
And change x to negative x. Okay, that's what this algorithm says. Okay, now clean it up. What's negative x cubed? Negative x times negative x times negative x is negative x cubed. So negative
Oh, I
y
see right
equals
there.
negative x
Yeah.
cubed. But if I multiply both sides by negative 1, I get back y equals x cubed. So I do get an equivalent equation. So that's what tells me I have origin symmetry. I replace both of them. Okay, and let me check.
I have a question. So I noticed that we got an even and odd function. So does it mean that an odd function is always symmetric with respect of the origin versus even functions?
Yes, we'll get to that later. That's a good point. So odd functions are functions and they have origin symmetry. Okay, right now we're not dealing with functions. So they could be functions or they could not be functions.
So odd functions always have a symmetric with respect of the origin.
Odd functions are symmetric with respect to the origin, yes.
Got it.
Okay.
And even functions, they're not.
Even functions have symmetry with respect to the
X or Y. Got it.
Okay. Question about if you're already at the origin. If you're already at the origin, well, if you reflect across the y-axis, you're still at the origin. If you reflect across the x-axis, you're at the origin, and if you reflect across the origin, you're still at the origin. So yeah, if your point is already at the origin and that's all you have, then yeah, it exhibits all three symmetries. I'm not sure if that answered your question. Somebody had that in the chat. But yeah, so if your graph, if all you have is the origin, then yeah, that has all three symmetries, because if you reflect across the x-axis and y-axis and the origin, you're still there. So yeah, you have all symmetries in that case. All right, so that was all I was going to do for today. I'm almost out of time as it turns out, but put this down. Okay, I mean, you don't have to copy it now. You can watch the video later and all this. And then starting tomorrow, I'll show you how to do some of these problems that are here. Okay. And I think that's it. Okay, so that was going to be it for today, folks. Tomorrow, so we're okay schedule-wise. I snuck in some of 1-4. There is no 1-5, so do 1-4 tomorrow, and we'll see how it goes after that. But yeah, after 1-4, we're going straight to 1.6. Okay, check the chat. Any other questions, please? Otherwise,
So
that's it.
quiz is from 1.3 to 1.6.
The quiz will be 1.3 to 1.6 potentially, yes.
Got it.
All right. All right, any other questions, please? All right, that'll do it for today, folks. So everybody have a good day, and we'll see you next time.
Thank you.
Okay,
Thank you, Professor.
Okay, bye, everybody.
Thank you, Professor.
See you next time.
Bye-bye.
Bye.